Okay, so I did the limit of a constant times a function as x going to a. This is going to be equal to the same constant times the limit of f of x as x approaches a if the right-hand side exists. Well, here I'm multiplying a constant times a function. What if I'm multiplying together two different functions? And I'm dedicating this clip to say, yes, you can. So this is limit law number 4, if you're following along in the book. If you take the limit of some f of x times some function g of x as x approaches a, this will be equal to the limit of f of x by itself, x still going to a, times the limit of g of x, x going to a by itself, so long as both of these limits exist. And this limit law, opens up a huge amount of new ground for us. No, really, it does. See, I'm going to take f of x equals the function x. And I'm going to take g of x also equals the function x. So this is saying the limit of the function y equals x squared as x approaches the coordinate a is going to be the limit of the function x as x approaches a times the limit of the function x as x approaches a. Okay, now I'm just being kind of boring. But the payoff is that I can combine this with my limit law number 8, the one that I said was the very most important. Limit of the function y equals x as x approaches a is just a. So this is an a, and this is an a. So the limit of the function y equals x squared, approaching any coordinate you like, is just that coordinate squared. You can just plug it right in. I like that. I like that I can just plug things in this way. It saves me so much time. Now, we got to be careful because not every function lets us do this. Not every function allows us to just plug in the limiting coordinate, and that'll be our final value. But the squaring function is one of the special ones that does have that property. And there's actually quite a lot of these. So I'm going to diverge from the text a little bit and say, well, if I can multiply an x times an x and I get an x squared, and this limit law works. I can multiply an x times an x. Yeah, if I can multiply an x and an x and get an x squared, I can multiply together an f of x equals x, a g of x equals x squared, and get the same rule for the third power of x. So the limit as x approaches a of the function y equals x cubed is going to be a cubed. Right? The same reasoning, I'm just not writing out all the steps this time. And I can keep going. Limit of x to the power 4 as x approaches a is going to be a to the power 4. This is going to save us a lot of time. So I can keep going with these. The rule that I'm getting at is as long as n is a positive whole number, then the limit of x to the power n as x approaches the coordinate a is equal to a to the power n. So every single power of x has this nice plug and play property. If I'm taking a limit, I just ask what is my final value for the x, and I put it into the formula. But that's not all. Because I can get this for every power of x, and the previous limit laws let me use this formula for adding any two functions, or subtracting any two functions, or even multiplying a function by a constant, that means that if p of x is any polynomial, any single one, then the limit as x approaches a of the polynomial p of x is just going to be p of a. So if I wanted what is the limit of the function 10x to the power 47 minus 17x to the 6 plus 5x to the 5 minus 4x cubed plus 27x minus 2. That's a polynomial. And I wanted the limit as x approaches, say, 10. I don't need to do the epsilons and deltas every single time. I don't need to draw the graph of this function every single time, though I'm sure this would be a neat graph to look at. I can just say, well, this is a power of x, so its limit is just going to be 10 to the power 47. And there's my coefficient. This is a power of x. Its limit is going to be 10 to the power 6. And there's its coefficient. This is a power of x. Its limit is going to be 10 to the 5, and there's its coefficient as well. And I can keep going down the line. It's a 10 minus 2. And there is the formula for my limit, for this polynomial in particular.